In this PowerPoint, my partner Sarah Oueidat and I, Yasmine Mounzer, are going to present the floating point arithmetic. I am going to go over the IEEE representation as well as the special values. I will also go over the addition and subtraction of floating points. I will finally give a real-life example about maintaining signal fidelity. Sarah is going to go over the multiplication and division of floating points and will give an example about the Intel Pentium. I will now begin with the first slide about the floating points representation. We will first discuss the IEEE floating point representation. We first start with the sign, which is 0 for non-negative numbers and 1 for negative numbers. Second, the exponent, represented in 8 or 11 bits, is the actual exponent plus the bias to ensure that the exponent is unsigned. For single precision, the bias is equal to 127, and for double, the bias is 1023. And finally, the significand, which is the fraction with the 1 restored, should be between 1 and 2. It is represented in 23 bits for single precision and 52 for double precision. Here are some special values. 0 denoted by an exponent and mantissa of 0. Infinity. The values plus infinity and minus infinity are denoted by an exponent of all ones and a mantissa of all zeros. The sign bit distinguishes between minus infinity and plus infinity. Finally, the value not a number, denoted by an exponent field of all ones with a zero sign bit or a mantissa that is not 1 followed by zeros. The steps of adding or subtracting two floating points are: 1. Compare the magnitudes of the exponents. 2. Align the binary points by shifting the number with the smaller exponent. 3. Perform the actual addition or subtraction. 4. Normalize the result by shifting the resulting mantissa and exponent. 5. Check for overflow or underflow, which will be discussed in the following slide. And finally, round the result if needed. An overflow occurs when subtracting a positive from a negative operand if the sign of the result is 0, or when subtracting a negative from a positive operand if the sign of the result is 1. In this slide, we will add two positive floating points, A and B. We first need to convert to binary. After inspection, we find that the exponent of A is 0,610, which is 126 in decimal, and B is 1 followed by all zeros, which is 128 in decimal. Therefore, we need to shift A by 2 bits. Now we have to perform the actual addition. After doing so, we are left with two options to get rid of the two extra bits. One, truncate, which leads to a result of 406,0000 in hexadecimal, and 2, round, which leads to a result of 406,0001 in hexadecimal. Both results have the same sign, which is 0 to indicate a positive result, the same exponent, but different fractions due to the precision error.
Hello Professor, this is Sarah Oueidat and I'm going to discuss the concepts of floating point multiplication and floating point division. And I'm going also to give a real-life example about where are floating point arithmetics used in real life. So, to start with floating point multiplication, we should follow the following steps. First, we should compute the exponent of the product by adding up the exponents, multiply the mantissas, and then normalize and round the final product. The next slide will have an example explaining those steps. So in this slide, there is a schematic diagram that sums up all the steps of the floating point multiplication in a summarized manner. Let's take this example whereby x is equal to 1.000 times 2 to the minus 2 and y is equal to minus 1.010 times 2 to the minus 1. So to start with, e1 is equal to minus 2, e2 is equal to minus 1. So when we add up the exponents, we end up with an exponent of minus 3. Then we should multiply the mantissas. Now, when we multiply the mantissas, we follow the regular binary multiplication, or we can use a simpler way, which is to transform the mantissas into decimals, multiply them, and then put them in a binary manner. And then we reach the result by rounding the product. So here the answer is minus 1.0100 times 2 to the minus 3. In floating point division, the first step is to compute the exponent of the result by subtracting the exponents. Then we should divide the mantissas and define also the sign of the result. So for example, if we're dividing with the same sign, then we end up with a positive floating point. And if we are dividing opposite signs, then we should have a negative sign. The third step is to normalize and round the resulting value if necessary. The next slide will have an example to illustrate these steps. Here is a schematic diagram that sums up all the steps of the floating point division. So let's take this example and apply it on the schematic diagram. Considering x to be equal to 1.000 times 2 to the minus 2 and y to be equal to minus 1.0100 times 2 to the minus 1. So the first step is to subtract e1 and e2. e1 in this case is minus 2, e2 is equal to minus 1, so the exponent is minus 3. And then we need to divide the mantissas. We can divide the mantissas as they are in binary form and give the result in binary form, or we can transfer these mantissas into decimal forms, find the result, and then transfer the quotient into a binary. So how is FP arithmetic used in real life? Floating point operations were executed by a companion chip, commonly called an arithmetic coprocessor, that was attached to the motherboard and designed to work in conjunction with the microprocessor. Eventually, floating point capabilities were integrated onto the CPU as a separate execution unit alongside the ALU. So if we consider the Intel Pentium and the figure of this slide, it contains two integer ALUs and a floating point ALU along with some other units. A microprocessor, as we know, it does arithmetic and logical operations on more than just integer data. So another name for a microprocessor is ALU. So ALU is a general term for any execution unit that performs arithmetic and logical operations on any type of data. So in our case, what we are doing is that we are doing FP arithmetic, which includes addition, subtraction, division, and multiplication, which is the duty of the ALU. The Pentium's floating point unit consists of only a single FPU, but some microprocessors might have more than one FPU.
And now back to myself, Yasmine, for the final slide, which is about maintaining signal fidelity using floating points. The engineers designing an audio signal chain in the analog and digital domains face multiple challenges. Audio signals have large dynamic ranges with information, which must remain uncompromised at both extremes of the signal range, the loudest and quietest. Throughout an audio signal path, the signal may be filtered, mixed, or amplified in multiple processing steps. In the analog domain, information was always prone to be lost by adding noise at the low end or clipping at the peak. A similar situation exists when the signal is handled in the digital domain. The data values that represent the content must stay within the overall number range if information is not to be lost by overflow or truncation. Multiple stages of signal processing involve successive mathematical operations. With a limited number range, care has to be taken that the sliding window of relative values stays out of the noise floor but below the voltage rail. Conventionally, digital signal processing devices that employ floating point arithmetic have been considerably more expensive than their fixed point counterparts. A frequently used methodology has been to develop an initial version of a signal processing project in the floating point environment, allowing numerical values to range freely within the vastly greater available numerical space. Then, when the algorithms are working according to specification, the prototype is converted to lower cost fixed point hardware.